I'm Matthew Suntup from Saber Astronautics. I'm one of the space engineers here, and we've got a few of us over here. Today I really want to talk to you about the mission design services that we're working on at Saber and starting to provide to people like you. So Saber is a space operations and analytics company, and our mission is to democratize access to space and reduce barriers to spaceflight. We've got 4 main areas that we're working in right now. That's mission operations, mission design, space domain awareness, and spacecraft diagnostics. And today I'm really keen to talk about mission design and talk about what we're doing on that front and how we may be able to support some of the ideas in this room today. So I'll go over a bit of the background of how we got into the mission design service and what's inspired it, then break down the actual mission design itself, some of the high-level concepts we look at when we're doing our modeling and analysis, and finally I'll just talk really briefly about some of the operations of it and how that fits in. So before we actually get into what Saber's doing, the big inspiration for this mission design service is actually the European Space Agency's concurrent design facility. So over in the ESA, they set up this concurrent design facility idea in 1998. The idea is essentially that you get a lot of experts in specific subsystems and specific domains, and they work on assessing future spacecraft missions. They've been really successful at this. They've actually done hundreds of them, and the list is really interesting if you come online. I was poking through this, and nuclear thermal rockets pops up, as well as in situ resource utilization for production of oxygen on the moon. There's a lot of really complicated and really cool things they're doing, and they're pretty much achieving all this by using a concurrent engineering methodology, which really means they're looking at all the aspects of that mission in parallel, and they're considering how everything affects everything else. So that kind of takes us to the Cubesat and small satellite conference that we're at. We're interested in these smaller satellites, and we need to consider, I guess, why CubeSats have grown so big in recent years. And the CubeSat revolution has really been driven by this idea that CubeSats are increasing our accessibility to space. So what Saber's looking to do is, inspired by this ESA CDF concept, how can we bring something similar to Australia, which is able to give a more accessible kind of avenue into what we're doing, into this design process, essentially. So I'll break down the general mission design process that Saber's offering. The way that we go about it is we essentially split researching, modeling, and reporting. So researching is this first aspect where we're working in really close collaboration with clients. This is generally looking all at mission objectives. So it depends what the actual mission is going to be, but for some clients this might mean, oh, you've got a really specific spacecraft instrument that you already know what you want to use, and that's going to be your payload. But this could also extend all the way to, oh, I've got a very general mission objective, like I want to look at specific areas of farmland in Australia. I want to look at specific wavelengths for those areas in order to monitor crop health, for example. And in that case, research is going to look down, what multispectral or hyperspectral cameras could we be looking at? And we might be picking COTS components or helping you look at other partners who can develop custom components for you. I'll skip over to reporting, because modeling's the interesting one. So reporting I do find interesting, actually, because we're looking at these 3 distinct but also overlapping audiences whenever we want to report at the end of this. So obviously you've got the engineering outcomes. That's what you need in order to continue development past your initial conceptual mission design phase. But beyond that, we also consider other audiences. So you'll have stakeholders like venture capitalists or grant providers, for example. And they might be a lot more interested in getting a high-level overview of the technical concepts and a lot more business outcomes specifically. And then we've also got regulatory bodies. So some people earlier were talking about ACMA and ITU and going for those frequency allocations. They often require pretty specific information, and that's another outcome of this kind of report. Modeling analysis is the real crux of what we're doing with mission design though, and I'll go a lot more into that. So essentially modeling analysis is, it has to consider a lot of different aspects of the mission and of your spacecraft all at once. This is kind of where concurrent design in, like as a concept comes in. So everything you're seeing on the slide pretty much needs to be done at the same time. If you affect one subsystem, say I make a change to a power subsystem, I need to increase the size of my battery. I'll expect that that affects a lot of my analysis, and that in turn will affect other subsystems. You know, now I've got a greater mass. Maybe my moments of inertia is run out. I need to consider different reaction wheels, things like that essentially. Everything needs to be considered all at once. If I go into these five really briefly, I'll give a bit of a high-level overview of what we're looking at. So payload analysis is all about mission objectives. We're pretty much looking at coverage, if I was going to say it in a single word. So if you're doing Earth observation, coverage could be, are you looking at the targets that you want to see? What are the revisit rates you're achieving? What resolution are you achieving? Are you getting those mission objectives that you set out to do? It doesn't have to be Earth observation though. So maybe you're taking measurements of the magnetic field of the Earth, or maybe you're looking out at space. Whatever it is, you'll have some kind of metric which we'd be able to measure the success or failure of your mission objectives by, and we are going for success. So orbital analysis is the next area. Essentially with this, the first thing we're looking at is things like perturbations. So depending on the orbit, you might find your orbital parameters change over the lifetime of a mission. In addition to this, you might see things like the orbital lifetime analysis, which is affected by atmospheric drag. And you have to consider how this is going to affect the payload analysis that we just talked about. If your mission ends early, or if you're thrown into different orbits over long periods of time, like how does that affect your payload analysis? In addition to this, we've got some radiation analysis. This is a really interesting area because obviously there's the one aspect where, oh, how long is my hardware going to live with the radiation I'm exposed to in my orbit? But beyond that, maybe your payload actually needs to get certain kinds of radiation. Maybe that's what you're out there to measure. So it all comes into your orbital analysis. The other point that I've skipped over so far is it's the constellation optimization. And right now this fits a bit into some of the things Aidan's going to talk about, which is also in some of the open source things that we also have. Maneuver analysis comes directly from orbital analysis. So some of the interesting things are station keeping, which looks at the lifetime analysis, perturbation analysis we just talked about. How much delta V do I need in order to mitigate those, if that's something I need to mitigate to meet my mission objectives? We've also got the orbit optimization, so thinking about sustainability and how much delta V you might need a budget in order to get back down to a position where you're guaranteed the orbit maneuver. Another really interesting one is the collision avoidance. So up the top when I was talking about the things Saber does, space domain awareness is one of those areas that we're really interested in. So we're able to use our conjunction tooling in order to get an estimate of, over your mission lifetime, how many collisions do you expect you might be subject to, and how much delta V should you account for of that mission in order to mitigate the risk of that actually happening. SATCOM analysis is really similar to payload analysis. In this case, your targets are your ground station. So you have a ground station network, and we're really looking at signal quality and whether you're able to meet the requirements of your mission in terms of the amount of data you may have to downlink, and whether you're getting enough opportunities to send up commands if you need to be able to control your mission as you go. Satellite design is where we start talking about actual components. So we're working a lot with commercial off-the-shelf components, but you can also bring in your own custom components, or your partners may develop custom components. And that's where all of this is analyzed, looking at the traditional spacecraft subsystems. We've got attitude determination control, command and data handling, power, propulsion, structural and thermal subsystems. And any changes here are going to affect your analysis as well. And that's where the automated tooling really comes in to try and help mixing all of this together. So essentially to summarize, at the end of this mission design process, what you end up with is a conceptual mission design that focuses at the start on collaborating with the client in order to develop those mission requirements. You move on to modeling and analysis, where you're developing some proof of the feasibility of the mission itself, and you're using the automated tool set in Saber. And then you've got reporting, which is to those different audiences we talked about before. But beyond mission design, I also want to briefly just touch on mission operations. So one of the advantages of doing mission design like this is that we're also going to come out with specific outcomes, specific data outputs that will aid in operations. So Saber operates missions out of the Responsive Space Operations Center. If you've been over to Lot 14 in Adelaide, you might have seen this. Essentially, we're using a whole different suite of software tools, including the predictive, interactive, Predictive Interactive Ground Station Interface, is a mouthful, or PIGI, and other Saber software tools. And essentially doing mission design with Saber will make sure that we have the outputs that our operators would need if you then want to go ahead to operations. And so the idea is that it kind of is all in a single solution. And yeah, that's pretty much it. If you're interested in doing a mission, please come chat. Will Zhang, who's a massive part of the mission design team, is also here, and he helped me massively with these slides, so I wanted to shout him out. Yeah.